Hi everyone. So this is topic number 23, and for topic number 23, I have chosen structure of metal cluster and the reaction of metal carbon. So this topic is actually a combination of two topics from organometallic chemistry, which is a very important chapter for CSIR-NET chemical sciences. So as we are targeting CSIR-NET June 2024, so actually not much days are left actually. So keep learning with me. So I have chosen the topics from organometallic chemistry such a way that you can solve as much as possible. You can solve more questions from organometallic chemistry because from this chapter many questions actually come in the exam. Okay. So please listen carefully. Today's topic is also a very important topic, and the structure of metal cluster actually related to the boron cluster, determination of structure of boranes, various boranes. So Wade rule. So I have previously uploaded videos on that. So please, if you have not watched that video, please watch it first because that is very helpful to understand today's topic. Okay. So let's start to today's topic. Hope you will enjoy this session. Okay. So now the metal cluster. So what is actually a metal cluster? That we have to know. So the molecular ion or neutral compound having three or more metals and having significantly metal-metal interaction. So from this definition, or these are some examples, questions will not come. But we have to have the idea about what we are learning, right? So that's why I have incorporated these parts in the PPT. Okay. So how to actually calculate the metal cluster, the structure of metal cluster, or how can we solve the problems? Okay. So that I will come into. So in this table, you can see here. So these are nothing but the we have previously read it in the boron chemistry, boron structures. So n minus 1 supercloso n is needed. N is what? N is number of metals. Okay. So we have to calculate something and then we can define the structure of that particular metal cluster. Okay. So for to remember this table, there was a trick, right? Thiol, SH, cyanide, and then aromatic heterocyclic compound, right? So that simple trick will help you to understand, to remember this table. And here nothing but we are starting with n minus 1, and then we just simply will add plus 1, then it will be n, then plus 1 will be n plus 1, then again plus 1, that will be n plus 2, plus 1 n plus 3, like that way. Okay. So simple. So if you know these things, the right hand side of the table, you can easily relate with this specific n values. Okay. Now the most important thing, determination of the structure of metal cluster. See how can we do that. So step 1, in the question actually one metal cluster, the formula will be given. Okay. So you have to calculate. Step 1 is the calculation of the total number of electrons for a complex. We have done it, right? How can we do that? We have done it in the case of 18 electron rule, but here only difference is here metal cluster we are using, right? So the formula will be a bigger one and the value of TEC will be also a big one, right? So for TEC, we know the formula: valence electrons of metal plus electron contributions from the ligands plus overall negative charge on the complex minus overall positive charge on the complex. Simple. So here one thing was there, the MM bond. We have to calculate. We had to calculate the MM bond also, but here we are not considering MM bond. Okay, metal bond will be not considered. Fine. Now step 2 is polyhedral electron count. If you see the formula, that PEC is TEC minus 12M. For the case of boron, it was PEC equals to TEC minus 2M. Similar, but only difference is here 2 we have taken, here 12 is there. How can we relate that with something? So for the when we are studying the isolable analogy, that time I told you that when for a main group, when we are actually relating for the isolable analogy, for the main group, if we count the electron that and found that it has 3 electron as a total, we related that with 13 electron. Like the same way, if 4 electron for the main group, that will be related with 14 electrons. So plus 10 will be added for the transition metal complex. Like the same way, if you can remember this formula for the boron, you will add the 10 here. So 10 plus 2, that will be 12. Right? Now we can understood this. And step 3 is the polyhedral electron count by 2. Like the same that was for boron. That's why I am telling again and again that you have to watch that previous video of mine. Okay. So that is the third step, PEC by 2. Then what value you found, please arrange that value according to the respective n values. N values you know, right? So because formula is given, so for formula, how many number of metal units are present? Metals are present. That is the n value. N means metal, and we can arrange this value with according to the n. How? Let's say PC by 2, we got this, and in the formula it is given, let's say RH6CO something X. Okay, so RH6 means n is 6. So now if we want to arrange this 7 value with respect to n, what will be? 6 plus 1 means n plus 1. Okay, so like that way we relate this n plus 1 with the, in the table we know it will be closer, right? So in this way we can determine the structure. Okay, fine. So now we will see and yes, recording is on. Fine. So now we will see one example. Okay, so this is the example. If we see here, okay, so first the number of meter. What is the number of meter here? N is 3, right? Okay. Now step 1 is the calculation of TEC. So we know TEC means total electron count. Total electron count means 3, the number of metal, and okay. So if you forget the table of 3D, then you can't solve any question from the organometallics or coordination. You have to remember that. Okay. So for 3D series, what was it? Scandium, titanium, vanadium, chromium, manganese, Fe, cobalt, then it was nickel, then copper, then zinc. Okay, this is D1, D2, obviously D1 4s2, D2 4s2, like that, D3, D4, D5, D6, D7, D8, and D9, D10. Fine, and you have to also remember the specific group wise what metals, transition metals are present. Okay, so you have to actually remember that. Okay, so TEC 3 into Fe means D6, right? But we will take the total electron D8 because the 4s2 electron should be also counted, and 12 into 2. Okay, so that will be 24 plus 24 means 48. Fine. Now step 2 is calculation of TEC, and TEC we know that this TEC minus, so TEC is 48 minus 12 into n. N is 3. So 48 minus 36, that will be what? 12. Okay. Now step 3 is PEC by 2. So PEC by 2. PEC we got 12. By 2 means 6. And now we have to arrange it with respect to the n values. Okay. N value is 3. 3 plus 3. 3 we have taken. And if we add 3, then it will be 6. So it will be N plus 3. What was it for N plus 3? Arachno, right? Thiol, cyanide, aromatic heterocyclic compound. So aromatic arachno. So arachno will be here the structure for this metal complex. I hope you have understood. Let's take another example. So this is the example. So I have to remove the everything. Okay. Oh, with eraser I can't do that. Okay. So now, okay. So OS5 C CO 15 will be there. Okay, 15, the correct thing. Okay, I have corrected actually. Previously, I have recorded once. That was not good. So step 1 is the calculation of TEC. We know, and which I was telling you that you have to have the idea that OS is from which group. How many d electrons are present? Okay, that you have to know. So it is actually, this is not the correct one. Fe, Ru and Os. Okay, this is in Fe group. So we know Fe is d6. So we have to take that only, and 6 plus 2, that is 8, and E2 5, and carbon 4 valence electron, and 15 into the 2 for carbonyl. It will be 40 plus 4 plus 30, that will be 74, right? Now step 2. Step 2 is the calculation of PEC, right? We know that. So PEC will be 74 minus 12 into n, right? 12 into here n is 5. It will be 74 minus 60, that is 14. Fine. Now step 3 is PEC by 2, right? PEC by 2 means 14 by 2, that means 7, and 7 is actually n, which is 5 plus 2, n plus 2, right? N plus 2 means what will be the structure? See the table, that means nido. So it will be nido structure. See, we have solved 2 problems. Okay. Now I have taken one previous year question. So only one question I have taken. Many questions are actually asked in the exam, but in this question, see what is the question actually asked? The cluster having arachno type of structure. Okay. So we don't know each option, actually we have to solve and see which are giving arachno. For that reason only I have taken this question. You have to solve the 4 things, so that the practice is actually very important, right? So for that purpose only I have taken this. So OS is in which group? Fe group, OS. So 8 into 5 plus 16 into 2. Fine. This is what? This is PEC. Okay. Solve it fast. 40 plus 32. That means 72. Fine. Now PEC. Second step. PEC means PEC minus 12n. 12 into 5. That means 60. So 72 minus 60. That will be 12. Now third step is PEC by 2. PEC by 2 means here 12 by 2, that is 6. And here n is 5. So it will be 5 plus 1 means n plus 1, that is closo. But we need arachno structure. So 1 is not a correct option. Fine. Let's come to B. B is given what? OS 3 CO 12. Okay, fine. Let's first calculate the TEC. TEC means 3 into again 8 plus 12 into 2. That means 24 plus 24 means 48. Fine. TEC will be what? TEC will be 48 minus 12 into 3, that is 48 minus 36, that will be 12, right? And PEC by 2 will be 6. So if you are thinking that here also the PEC by 2 was 6, and here also in the second option PEC by 2 is 6. So both are same, and it will be not the correct option because A was not correct option. If you are thinking like that way, you are wrong. Please understood this, because here n value is different. Here n value is 5, and here it is 3. So when we arrange in the last step, when we arrange the value and see that what is the structure of that cluster, that time it will be different, right? Here n is 3, so I have to arrange it like that way. 3 I have taken for n, and 3 plus 3 it will be 6, so it is n plus 3. That means it is arachno, right? It is arachno. So B is the correct option. But as you are practicing, I will solve the other options also, so that you can practice with me. Okay. So let's just take the eraser. I will just remove everything here. Okay. First I will see. Yes, recording is on. Fine. So resume, and eraser I have taken. So it will be, this all will be different round. So this will be also different, this will be different, this will be different. Fine. PEC means 12 into n different, this is also different. Okay. This will be different, this will be different. PEC by 2, this will be different, this will be different, these all are different now. Okay. And that's for the second case also. Okay. Because 4 options are left now, so that's why I am just removing parts. Fine. So it is 12 into n. Here value will be there. Here is also the different value should be there. Here PEC by 2 will be different. It is also different, and this is also, and again this. Fine. Now we can solve this, right? Okay. So third option C. C is IR4 CO12. So for you only, I have taken this table so that you can relate. So IR is in which group? IR is in cobalt group. Cobalt means 9. 9 into 4. Okay. TC plus 9 into 4 plus 12 into 2. Right. So 36 plus 24. That means it will be 60. And PC is 60 minus 12 into 4. 60 minus 48. That means it is 12. PEC by 2 is 12 plus 2, that is 6. And 6 is, here n is 4. So 6 is 4 plus 2, like n plus 2. That means it is neither. Obviously it is not correct option. Okay. For the D case, RH 6 and CO 16. RH is in which group? See, RH is in cobalt group, right? So we have to take 9 for RH into 6 plus 16 into 2. That means 54 plus 32. That is 86. Okay. And sorry, here 86 will be there. And here 86 minus 12 into 6. That means 86. Okay. 86 minus, that will be 14. Okay. It is 14. Right. And PEC by 2 means 14 by 2, that is 7. And here n is 6. 6 plus 1 is 7. So n plus 1, that is closer. See, we have solved 4 options, but we have previously already found that B is the correct option. Okay, fine. Now coming to a different topic, that is reactions of metal carbonyl. That is also a very important topic to solve many questions, that we should know that how metal carbonyl actually reacts. Okay, when any condition is given, other ligands are given. Okay, let's just see that. So reaction of metal carbonyl for substitution reaction. So we have to have the idea that what is actually a substitution reaction. So when one group from a molecule is replaced by other groups, that is called a substitution reaction. For example, when we take that any organic molecule, let's say R and X, that is a leaving group, and Y group is given. So this is X is actually replaced by Y. These kind of reactions are called substitution reaction. So I think you know, all of you know these things, right? Because you are reading chemistry, you are now a MSc student, so you should have an idea, right? So uh, mm, this is like a when a football group. Okay, so one player actually has a fracture in his leg. Okay, so he can't walk or he can't play, right? So coach, what actually coach is doing, coach will find another boy who can able to play in a better way. So he will find a replacement, and the boy is replaced, the sick boy. Okay, like that way actually substitution. So that new boy is the substitute of the sick boy, right? So that is the thing here. So Y is actually substituted X. So for the metal carbonyl, for example, when PPHC, let's say, is given PME3, okay. So one CO actually left, let's say 6 CO, okay. So is left and PME3 actually added. This is actually a example of substitution reaction. But we have to have the idea that how the reaction is happening. So there are two ways. Okay, one is dissociative, another one is associative. So let's just talk about the dissociative mechanism. In the case of dissociative, what has happened is that first dissociative means dissociation. Dissociation of what? Metal ligand bond. So first dissociation will happen. The leaving group will leave, and then the association. Then the new ligand will sit on the metal. That is the thing. Okay. So when actually what kind of complex will show the dissociative mechanism? Complex having 18 electrons are stable. We know we have solved 18 electron rule for that reason only. So it can't take any electron from the incoming ligand. Okay, it doesn't have any urge for electron, right? So at first, one for that kind of ligand, first one ligand will be removed so that it will goes towards 16 electron or something like that, so that it has now urge of electron, and then the electron or ligand will sit on it. Okay, so it will proceed to dissociative mechanism. So the steps we should know. So step 1 is here the dissociation, right? And step 2 is the new ligand coming. Okay, so most important thing is that here slow step is the dissociation step. Okay, means rate determining step, RDS. I have talked, I have also made one video, many videos from kinetics. So there only I have given that idea also, that slow step, how, why slow steps are actually rate determining step. Okay, I have told one simple example for that also. So RDS means rate determining step. So rate actually depends on that step. The okay. So that is the thing. So for the associative mechanism, what will happen? Complex having less than 18 electrons. So first association. Associative means first association. Then CO will be removed. Okay. So complex having when what kind of complex will show this? So this is opposite of dissociative, right? So complex having less than 18 electron will proceed through that dissociative, but there are exceptions, right? What kind of exceptions? Complex having 18 electron can also proceed through the dissociative mechanism. We know that for the case of 18 electron, this will be associated. Okay. this will be nothing but associative. Okay, you will be confused with it, so I am just right now I'm changing that. Fine. So this will be the case and recording is on. Fine. So okay. Complex having 18 electron, we know that if we have less than 18 electron, that time associative mechanism will happen, and when 18 electron is present, that time dissociation. But the exception is complex having an 18 electron rule, 18 electron can proceed to the associative mechanism when metal has one flexidented ligand. Okay. The flexidented ligand also I have taught you in the when I was teaching you the various kind of ligands, the isomerism in coordination complex. Okay, in that video you will find that what is flexidental ligand. I will tell you here in a short way that flexidental ligands are actually capable of changing their hapticity. Right? What is hapticity? The atoms ligand actually attaches with metal, that we know, but with how many atoms? How many atoms are of ligand which actually attaches with metal? That is the hapticity of the ligand. Okay, so flexidented ligand actually can change their hapticity, can change their connection with metal. Okay, so according to the requirement of the metal. Okay, so it can show that eta 1, eta 2, let's say, it depends on the ligand structure, eta 3, eta 5. Okay, so not in a single time it will show this all behavior, but it can actually change. Okay, according to the requirement. That is called this flexibility, right? Flexibility. So flexidented ligand. For example, the CP we know, right? It's a very famous ligand. Let's say this is metal. So this, like this way, if we represent, that means it is attached with, the metal is attached with 5 carbons of the CP. That means this ligand, CP ligand here showing eta 5, but it can also show the eta 1, that is like that. This is eta 1 and also eta 3. Eta 3. Okay, so it is eta 3. So this 3 actually it can show. So according to the metal's requirement, it can change its hapticity. Okay. So coming to the dissociative mechanism, the step 1, no, right? Associative. Associative mechanism, the step 1 is the slow step. What is the attachment of the new ligand? And step 2 is the after attachment, it will remove. It is a fast step. Okay, so slow step means it is the rate determining step. So rate of the dissociative mechanism will depend on the association of the new ligand. Fine. Now remember, this is very important. The rate of the associative mechanism is higher than the rate of the dissociative mechanism. Why? Because for the associative mechanism, the slow step is the attachment of the new ligand. Okay. But for the dissociative mechanism, the RDA is the breaking of MCO. And breaking of MCO bond is very difficult than the other molecule breaking or other ligand breaking, because we know metal, when carbonyl actually bonded with metal, that also I have taught you. Okay, that also I have taught you when I was teaching you the carbonyl chemistry, carbonyl bonding with metal. Okay, in that video. So when actually it is bonded with metal, it donates to sigma donor, but it is pi acceptor, means metal electrons will be given to the its pi star orbital. Okay, which means this bond, MCO bond, metal to carbonyl bond, it has now some kind of double bond character. So it is strong bond than the other metal ligand bond. Okay, so removal of CO is a bit difficult than the association of new ligand to a metal. Okay, So that plays a major role here, and please remember that rate of the associative mechanism is higher, because in many questions it can given many reaction. So you have to calculate first the electron count for that complex, right? Then you can understood that if it is 16 electron, it can go towards associative because it has less than 18 electron. And if one complex has 18 electron, generally it will go towards dissociative, right? So for that case, if you are asked that which is a faster reaction, which will give product in a faster way, you will answer the 16 electron species, which goes through associative mechanism. Okay. Now coming to some example. So I have taken this example. So PME3 is given, 3 molecules of PME3. So first I will draw the structure of CrCO6. That is like this, octahedral. So these are equatorial CO and axial CO. So in the starting, there is no difference between equatorial and axial, right? It can be exchanged also. So first PME3 is given. So if it is associative or if it is dissociative, the substitution will happen, right? Let's take that this CO will remove first. Fine. So PME3 will sit here, there, right? So CO is there. One PME3 will sit here. Another CO, another CO, another CO, CO. Okay, that will be there. Now, second step, another mole of PME3 will come. Now, there are two different kind of COs are present. One is trans to PME3 and another 4 are cis to PME3. Okay, so these 4 are actually same and this one is other kind of CO. So two kinds of COs are present. So which CO actually be removed? That you have to consider. So I have told you in the case of that CO back bonding and how actually how the spectator ligands affect the metal CO bonding, that I have told you. So what will happen for the kit base of PME3, because here the only difference is PME3 is present, right? So COs are actually the sigma donor pi acceptor ligand, which actually draws electron density from the metal, and PME3 is a sigma donor ligand, which doesn't draw any electron from the metal. Instead, it will increase the electron density of metal, which result if the increase of electron density is there in the metal, it will give the more electron towards back bonding, right? Back bonding of, it will give more electron towards the pi star orbital of CO, and as this CO is trans to this PME3, the effect will be more for this trans CO. Effect means the metal, now the chromium metal will give more electrons towards its pi star orbital, means back bonding is more here. So it has more double bond character. So which means the CrCO bond is more stronger here, more stronger bond because of the trans sigma donor ligand PME3, right? So as compared to these MCO bonds of the equatorial CO, metal CO bonds, this is more stronger, so it will not leave now. So another CO which are in the from the equatorial, that will leave. Okay, so this CO will present. So let's say this is removed. Okay, so PME3 will sit here. So other COs are there, CO, CO and PME3. Fine, right? Now again another mole of PME3 is given, right? Now what will happen? Again this CO is now, what kind of COs are present? Let's first see that. This is trans to PME3. This is also trans to, no, not this is. Okay, So this is trans to PME3 and this is trans to PME3. So these two are same kind of COs, but these are actually cis to PME3. This is cis, this is cis. So these are a type of CO. Okay, with these two symbol I have shown to you. These two are same. These two are same. So which kind of CO will remove now? See, these are trans to PME3. I have shown to you the COs which are trans to PME3 that has more stronger metal CO bond. So this is stronger, this is stronger, this is stronger. Both are stronger. So these or these will be removed. Any of these. Okay. So CO will present, CO will present. Let's say this actually remove. So it will be PME3. PME3 was present, PME3 was here present, and here CO. Now see what kind of isomer this is. I have taught you. For these cases, this kind of isomer is called facial or FAC isomer. So FAC isomer will form. This can be also a question. You have given this and you have to choose the answer. Many kind of isomers can be given and you have to choose the FAC isomer. Right? Clear? So I think you have understood this. And another question can be there. Let's say this rate is K1, this is K2, this is K3. So the fact is that it is it can be seen that K1 is greater than K2 greater than K3. K1 has the highest rate because see, we can explain it like that way that all COs were present, which draws actually metal electron density in its pi star orbital. So 6 COs were present. So that time metal has less number of electrons here because electrons are drawn here. Okay. So when PME3 comes with with 2 electrons, now metal has more urge towards electron, right? In the first step, so it will accept easily the PME3. So reaction is faster. Now for the second case, what is happened is that here now less number of CO is present and PME3 is already there to decrease its arch of electron. So in this case, the rate will be a little slower than the first step. And the case of third step, it will be even slower. Okay, so that is the thing here. So let's see first that here is a D4 metal, right? So 6 electron and 6 carbonyl is present and 12. So it is 18 electron species. And for the case of 18 electron, one exception is also there, that if it has flexidented ligand, that time it can show associative because associative mechanism is faster than dissociative. But here no flexidented ligand is present, right? And it is 18 electron, so it goes through dissociative mechanism. That can be also a question. So what we have read here from this slide, so as it is 18 electron rule and doesn't have any flexidental ligand, it will show mechanism via dissociative, and the K1 will be greater than K2 and greater than K3, and what isomer will form in a major amount. Okay, if you understood all these facts, right? If you have understood these all, you doesn't have to remember anything. Okay, so you have to have the clear idea about all the things happened here, right? See another example. This example is very interesting because it is actually a flexidental ligand. Let's say let's say it follows 18 electron rule. Okay, so how can we say that? Then what will be the metal? From 18 electron rule we can calculate that. So this is connected to 5 carbon, so we have to take 5 electron from that, and metal, let's say x number of electron we have to find out, and carbonyl is 3, so it is 6 and it is equal to 8. That means x will be 7, right? 7 means the 5 system. So let's say manganese is there, it is only given. So you have calculated and you know that it is 18 electron species. So you will say it is 18 electrons, so it will go through dissociative. It can't take electrons from the ligand, but that is wrong because here one flexidental ligand is present, which can show various kind of hexicity. Okay, so it is eta 5. I have previously told that CP, this is like a CP ring, right? So CP ring can show eta 5, eta 3, eta 1. Okay, so before going attaching with PME3, it will just convert it, the bonding of with metal Mn, convert it in eta 3 form. Okay, so how can we write that? This metal, sorry, this is again the same thing, right? This is what will happen here, 5 member. So eta 3, this is now eta 3, so eta 5 to eta 3 conversion will happen. Okay, so after eta 3, it will be now 16 electron species, CO and CO. So it is Mn, right? So 7 plus 3 and 6, it will be 16, right? So 18 to 16 and then PME3. Actually, we can show it in a one step only, but for your understanding purpose only, I am writing like that way. M, CO, CO and CO, PME3. Okay. So associative mechanism, first association and then dissociation of CO, right? So after dissociation, CO, CO, PMH. So see, I have changed the hapticity again. So after when the dissociation will happen, that time where I like. So eta 3 to eta 5 again, that conversion will happen. So see, now 5 plus Mn, it is Mn, right? Mn. So 7 plus 2, 2, 2, 6. That means 8. See how easy this is. If you understand the fact that this is flexidental ligand and it can show eta 3 also, so it will goes via associative, because we know that associative mechanism is faster and easier. Okay, so it goes through associative mechanism, where slow step is this one, the joining of the ligand PME3 new ligand. So this will be the slow step. That associative mechanism will happen in a faster. Fine, because you can have the question that if it is showing 18 electron, it can go towards a dissociative, right? So it can go, but if it has any tendency or the chance, any chance is there to for the associative mechanism, then obviously associative mechanism will happen first. Okay, so here one chance was there to after conversion of eta 5 to eta 3, so that's why it goes through associative mechanism. Okay, so it is very interesting and important also, so please see it in a careful manner. So I hope you have understood this session, and this is not a very tough session, I would say, but your patience is needed for understanding a brief idea about this, to have the idea about all the things. Okay, so I hope you have enjoyed this session. Please, if you have any question, please comment down below. I will check and I will try to answer that one. And please practice more these kind of questions. Okay, previous year questions you have to practice more, so that you can solve the question in a efficient way in the exam hall. Okay, not much time is actually left, I will say. Please practice more. Okay, see you in the next session. Thank you so much for listening.